ROS interfaces are at the very core of what makes ROS a powerful tool. In this video, I'm going to start with the basic definitions for how to define and use ROS interfaces and take you through all the complexities, getting to best practices for how to design them, all their strengths and their weaknesses. This is the ROS Interface Primer. Who am I? My name is David Liu. I've been a ROS developer and maintainer for the past 15 years and am currently an independent ROS consultant at Metro Robots. Robotics, by its very nature, is a multimodal system. There are sensors, actuators, and all the programming logic in between. And each piece might have a particular programming language that works best for it. All the different programming languages need to be able to communicate with each other. Furthermore, because components of the robots can change, be it software or hardware, it is useful to have the communication be reusable. So ROS interfaces are defined communication pipes for propagating information between different programs. Say we want to communicate the Cartesian coordinates of a point in three-dimensional space. We need three numbers for that, an x, y, and z coordinate. We call this grouping of info a message. A message is one of the three types of ROS interfaces. This interface is already implemented in the package geometry messages as point. The message defines the type of information being conveyed. We can also define the specific communication channel with a name called the topic. We have different mechanisms to send, aka publish data on a topic, and to receive, aka subscribe to data. For example, we can publish a point in Python. We import the message type, set up the publisher using the message type and the topic, and then populate the fields of the message data structure, and then publish it. And then we can also receive that same point in C++. First, we include the message type, then we define a callback, what we want to do when we get the message. Here we just print it out. Then in a separate part of the code, we create the actual subscription using the message type, the topic, and some information about the callback. Thus, we can communicate between the two programs written in different languages using a common interface. We could also easily swap out either program for a different program that does something similar in a different language or performs a different function on the robot. And that's actually all the code we're going to see in this video. The rest is talking about the actual interfaces themselves. Now, let's take a step back and talk about why ROS interfaces. So reason number one is this is a defined data type. You cannot arbitrarily add an additional field or make other changes without changing the message definition. This gives a foundation of many common interface types that have become standards, leading to more predictable behavior and a shared ecosystem. Reason number two is that this is quicker and more compact than a less defined communication interface like JSON. So point.message has three 64-bit fields totaling 192 bits or 24 bytes. Meanwhile, this particular representation of in JSON takes 61 bytes. And checking the exact syntax of the JSON takes time, and there's no guarantee that the fields we expect will be in that message, nor that there won't be any additional fields. And then the next logical question is, why not use a different cross-platform structured data format like protobuf? First, it's important to note that ROS1 predates many of them, coming around in 2008. Protobuf also went public July 2008. 0MQ, its 1.0 was in 2009. MessagePack, also 2009. BSON, 2010. And ROS2 does build on an existing structured data format from Data Distribution Service, DDS, for reasons that are too complex to get into here. All that is to say, you don't have to use ROS interfaces, but it does give you an efficient communication standard that you can build upon. Plus, there's lots of existing ROS tools that you can use with them. Now we're going to start exploring the interface definition language, or IDL. And the first thing we're going to look at is the definition of our point message. The definition is a text file in the geometry messages package at msg/point.msg. We start off with a comment That's any line starting with a number sign. And then the other lines define the type, in this case float64, a 64-bit floating point number, and the name of the field, in this case X, Y, and Z. A note about field names: they can be alphanumerics and underscores only, has to start with a letter, do not end with an underscore, no consecutive underscores. Generally, these are words separated by underscores. And here's a couple examples. Now let's talk about the different types that are available in IDL. Here is a table of the primitive numeric data types organized by number of bits, 8, 16, 32, or 64-bit representations, and numeric type, signed and unsigned integers, and floating point. These are automatically converted to some corresponding type in each programming language, i.e. float64 becomes a float in Python and a double in C++. Here's another example using different primitive data types. From the package built-in interfaces, we have time.message. This has a signed integer component for the number of seconds and an unsigned integer component for the number of nanoseconds. The definition of time uses 2 integer fields instead of 1 floating point field to standardize the precision and to avoid floating point calculations. In ROS1, time and similarly duration were primitive data types, but in ROS2 they're not. They use the definitions found in the built-in interfaces package. In addition to storing numeric data types, there are also non-numeric primitive types that you can use. There's bool, a simple true-false flag, 1 bit. Byte and char, these are 8 bits with slightly different corresponding data types. String, which is a very common data type with possibly unlimited size. And W-string, I didn't actually even know this existed. This is a string with 16-bit characters. And if you didn't know it existed either, how rare is it exactly? Well, we can look at the relative frequency of all the different types. This is based on all the interfaces released with ROS Hydro. This table answers the question, how likely are you to find a field with a primitive type somewhere in a given interface? The top 3 most frequent are uint8, string, and bool. After that, there are the rest of the numeric data types. At the very end, we have the 8-bit types byte and char, which are barely ever used, and W-string, which is only used in example interfaces. Now, in addition to all the primitive types, we can also include other messages in our messages. So pose.message conveys a position, point, and an orientation as a quaternion. The type of the field is now a package name and a message name combined with a slash. You can sometimes get away with not writing the package name and the slash if the other message is in the same package, but I wouldn't recommend it. Also note, you cannot have a recursive message definition. In this example, I've made up a linked list node message that contains a linked list as one of the fields. This results in an error. Now, most of the time there'll just be a couple layers of composition, but you can represent quite complex data structures this way. The message with the most layers that I've found comes from the European Telecommunication Standard Institute Intelligent Transport Systems. Their message definitions, they have 16 layers of composition for the collective perception message definition, which is way more than I've seen in standard. One of the most common messages you will see included in other messages is the header. This is in the standard messages package. The timestamp provides information about when this data refers to, and the frame ID provides the spatial frame of reference for the data. As an example, let's look at point stamped. The convention is adding a header to a message called X is to call that new combined message X stamped, but it isn't strictly required. Messages using different headers generally shouldn't be compared directly without using the TF library to figure out their relationship in space and time. Thus far, all of our fields have been variable, meaning we can assign them any value we want. We can also create constants with values that never change. In the IDL definition, this is written as type name equals value. For example, float64 pi equals 3.14. The name of the field is usually written in capital letters to denote that it is a constant. This is frequently used for enumerated types, or enums, where a variable can have a set number of predefined enumerated values. For example, in movement messages, we have error codes, and that message only has one variable field, int32val. That field will be set to one of the constant values also defined in the message, including success, planning failed, or timed out. And there's nothing strictly forcing it to be one of the enumerated values, but if it does match, then we know semantically what went wrong with move it. Sometimes, if there's multiple variable fields, the constants will be prefixed with the variable's field name. For example, in sensor messages battery state, there are three variable uint8 fields: power supply status, health, and technology. And there's a different set of constant values for each of these variables. For the status, there's one for charging and discharging, as well as a couple others. And then for health, there's good, overheat, and so on. One of the new features of ROS2 interface definitions is allowing fields to have default values. Normally, all fields start as 0, false, the empty string, empty array. But if a literal value is given after the field name without an equal sign, that's that field's default value. That's the key differentiation between constants and defaults, is defaults have no equal sign, constants do. For example, sensor messages quaternion interface has 4 fields. Geometrically, initializing all the fields to 0 does not make sense. So adding the default value of 1 to the W field with the rest defaulting to 0 makes it so that the default expression of this message is valid. One last wrinkle to the IDL definitions is arrays. Any field can be changed to an array of values by adding a pair of square brackets between the name and field, i.e. int32 square bracket data. This changes it from having one value to having 0 or more values. For example, let's talk about the state of a joystick, sensor messages joy. It's got a header and then an array of floats that say the state of the different axes of the joystick, and then an array of integers to say the state of the different buttons. Joysticks can have any number of axes and buttons, so having these fields be variable length allows us to use the same message definition for multiple types of joysticks. The most common way you'll see arrays in messages are unbounded, like in the above example where you can have 0 or more values. You can also define arrays with a fixed length by placing an integer in between the square brackets. For example, we have this mesh triangle message. Since triangles have exactly 3 indices, the length of the list for a single triangle should always be 3. Very rarely you will encounter bounded arrays which have a maximum but still dynamic size. For example, here we have float64 less than or equal to 3 dimensions, or as many as 3 dimensions, but that's less common. How common? Well, overall, approximately 30% of messages have some sort of array in them, and this chart breaks down the frequency of each type of array in the released Humble interfaces. It's mostly unbounded, with a few fixed and a couple rare bounded arrays, many of which are actually just test messages. All these types of arrays give you the power to create much more semantically rich interfaces, as we'll see in a little bit. Now, messages are great for one-way communication, but sometimes you want to know that the message has been received, or you want to know the result of some calculation. For that, we have the two-part service interface. Defined in the SRV folder, the two parts of the definition are separated by a line with 3 hyphens on it. The first part is called the request, and the second part is the response. For example, here we have the set camera info service. The first part, the request, is just the camera info defined in a separate ROS message. And then we have 3 hyphens Then the second part is the response, containing a Boolean flag to say whether the camera info was successfully set and a string with any additional status information. One program puts the camera info into the request and sends it to another node. The other node will attempt to change the camera info and then send back a response with the field set to let the first program know whether that was successful or not. Here's another example that sends back even more information. In nav messages, we have the service getPlan. In this scenario, one node specifies the start and goal positions and a tolerance parameter in the request, sends it to the other node for it to do path planning with, and the path gets returned in the service's response. The service name by itself, for example, getPlan, is usually used in setting up the service and the service client. There are also separate data structures for the request and response within the namespace of the service, e.g. getPlan.request or getPlan::request, depending on the language. Now, services are great for relatively quick queries where it's fine for the program that sends the request to wait around until the response comes back. For activities that will take a considerable amount of time, it can be useful to have feedback on how that's going. If we consider the two parts of the service to be before and after, an action has three parts corresponding to before, during, and after, with each part of the interface still separated by a line with three hyphens. The first part is called the goal, the second part is the result, and the third part is the feedback. So it's actually probably better to say before, after, during. So here's another navigation example. In nav2 messages, we have an action called navigate to pose. In the goal, it specifies the pose to be navigated to and some behavior tree info. The result specifies an error code and a message. And finally, the feedback has a number of different pieces of information that can be useful while the action is progressing. And the feedback can be published as many or as few times as desired between the goal and the result. Now we have discussed most, if not all, of the features of the ROS Interface Definition Language specification. Of course, there is a separation between what is possible and what is good practice. So here we move out of the exact mechanisms of syntax and further into the realm of opinion. Your mileage may vary. So, big question number one. How many separate topics should I put my information in? There's a couple of different styles used in different places in the ROS ecosystem. I've given these general names. So style number one is the self-contained mega message. All the information needed for understanding the content is present in one message. For example, we have the laser scan message. Note that header.stamp, ranges, and intensities will pretty much always change message to message. All the rest of the fields are likely to stay constant. Now the benefit is you can understand everything by looking at any of the individual messages. The drawback is there's a lot of wasted bandwidth. You don't need to transmit the minimum angle on the 500th message. And this redundancy leads us to our second style of messages. So the second style I'm calling data and info. You separate the data that changes frequently from the constant data, which goes in a separate message. For example, we have the image message, which contains the value of each pixel, and the camera info message, which provides information about how the pixels relate to the real world, i.e. the projection matrix. The benefits are this is a more compact representation, a lot less waste, but the drawback is you need messages from two separate topics to fully understand the full context. Style number three I'm calling progressive messages. This is not super common, but you use two different message types to transmit the data and the changes to that data. For example, we have the cost map message, which contains an entire grid's worth of values and metadata. And then cost map update contains a rectangular patch of data to update within that larger grid. Most of the values stay the same in the larger cost map, and we only need to transmit the ones that have actually changed. The benefits here are very large bandwidth savings if some values do not change frequently. Drawback, we need all the messages in sequence to get the full current values. Now this approach was easier in ROS 1 because when you created a publisher, you had an option to add a callback for when a new subscriber connects. Thus you could send the entire grid to just that subscriber, and then you wouldn't need all the previous update messages. This was used to publish occupancy grids and occupancy grid updates in the ROS 1 nav stack. And to my knowledge, this functionality has not been replaced in ROS 2. All right, big question number 2 is, do we really need all this structure? In one sense, you only need one type of message, string. Any sufficiently useful data structure should be representable by a string, be it JSON, XML, YAML, Morse code, etc. We can use the string interface to pass messages between the different nodes, so that should be good, right? It's good enough for URDF and the MoveIt standard SRDF. These are always published as string messages in ROS. And the no fixed structure means flexible architecture. However, that also results in higher processing time for parsing the string, wasted bandwidth, and unpredictable behavior. The answer is clearly not that strings can never be used in messages. There are distinct uses. For example, human-readable debugging, unique hashable identifiers, and recursive data structures like URDF. On the other hand, strings should be used with caution. I'd say consider using constants to create enums rather than complex strings. Status codes are often more helpful than status messages for dealing with things programmatically, as long as you clearly define what the status codes mean. On the flip side, you can create too much structure. Complexity can make your interfaces harder to understand, use, and debug. It can also make the values harder to read without a library. The perfect example of this is the various ways that multidimensional arrays are codified in ROS interfaces. In the ROS IDL, you cannot just declare a multidimensional array in the message type like you would in C++. So you're allowed to make a one-dimensional array like this vector, but you can't make a two-dimensional array like a matrix. If you try this, the compiler will give you a message saying that this is not valid. You could define custom messages to represent the different dimensions, i.e. have a matrix be defined as an array of rows, and each row has an array of values. Note, however, there is no constraint that each row will have the same number of values. It is much more common, especially with two-dimensional arrays, to simply use a single array and define the row length. So here are some two-dimensional examples. For example, pose with covariance. This has a pose and a covariance matrix with exactly 36 elements. And row major here means that the rows are grouped together, i.e. the first 6 elements are the first row. Here, the row length is predefined as 6. To convert from matrix coordinates, a row and column, to an index into the covariance array, simply multiply the row by the row length and add the column number. To convert the other way, division and mod. Another example is how occupancy grids are stored. The row width is defined in the map metadata, and all the values for the grid are in the data array. Now, images are a bit trickier because you have a two-dimensional image where the pixel is represented by an array of different values, red, blue, alpha, etc. So the image message represents this as a three-dimensional array packed into a single array. This allows for flexibility to use the same message for multiple different encodings. If the encoding is RGBA8, then the first 4 values of the array will be red, green, blue, and alpha values for the top left pixel, followed by the 4 values for the next pixel in that row. If the encoding is RGB8, then the top left pixel will only use 3 values, red, green, blue, followed by the next pixel in that row, and so on. The pros here is that you get a lot of flexibility in the encoding options, so there's no wasted space for an alpha channel that wasn't used. However, it requires math to convert the coordinates. It's harder to read the raw values and understand where in the matrix you are. If you look at a random slice of the array, it's not clear which of the values are the red ones. And our last example for multidimensional arrays is the point cloud. A point cloud is an arbitrary list of points where each point might have some additional properties, color, depth, etc. Now the first iteration of this was the point cloud message. You had an array of points and an array of channels. So if you had 5 points, each with an associated intensity and distance value, then the length of points would be 5, the length of the channels would be 2 for intensity and distance, and the length of the values in each channel would be 5 for each of the 5 points. This representation had 2 key problems. Values for a single pixel were not clustered together, making memory access for things like filtering a lot harder. And the data associated with each point looks to be constrained to a float 32. Now in practice, the color was encoded in a channel named RGB, and the bits of that float 32 were then interpreted into a 24-bit color value, which is a bit misleading and kludgy. The modern version of this is the point cloud 2 message, used in ROS 1 and ROS 2. That's not what the 2 means. So here we have a header, a height and a width, and a list of fields, and a big array of data. Note the point cloud can be arranged in a 2-dimensional way, which is why it has a height and a width. Note number 2, the number of bytes per point is completely flexible and determined by the point fields. So here you see the different point field values. The point field basically has a name and a data type. And so although point cloud 2 says uint8 bracket data, it's not actually a list of unsigned integers. Those are actually raw bytes that can be interpreted as integers, parts of integers, or parts of a floating point field. The result is a very space-efficient message. It's very flexible and darn near impossible to read without a library. In the end, you can get very flexible behavior from the extreme interface types. Extremely simple interfaces like strings have to be interpreted. Extremely complex interfaces like point cloud 2 also have to be interpreted. When possible, it's much easier to have a defined data structure. I much prefer a point with defined XYZ fields to an abstracted generic point data structure with a flexible number of dimensions that's defined at runtime. Big design question 3. How do you design flexible interfaces that can be used in multiple configurations? Another way to look at this is, how do I make a component of a message optional? Turns out there's a lot of different ways. I've identified 9. Option number 1 I'm calling fat messages. Have every possible component that you might want as part of the message, and just ignore certain components if they have a special value. For example, in battery state, there's temperature and current, but we ignore these if they have the not a number value. Option 2 is you could have flag-controlled interfaces. The value of one field dictates whether another component has a real value or not. It could be a Boolean flag. For example, in the compute path through poses action, we have an optional start pose, and whether we use that or not is dependent on the Boolean flag useStart. This can also be dictated by some enum style field. For example, in marker, the message, the string field text is only used if the type is equal to text view facing. Option 3 is parallel arrays. Ignore arrays with no elements. So consider the joint state message. Here we have some number of joints, call it n, with names defined in the name array. The positions of each joint are defined in the position array, which should also have length n. If the velocity is measured, then the values go in that array, otherwise the array is empty. Likewise effort. This is also seen above in the point cloud message as we discussed earlier. Option 4 is flexible length arrays. The IDL allows us to bound the maximum size of an array, so we could just make up the definition for a single joint state with an optional velocity like this. So it has a name, a position, and less than or equal to 1 velocity. I haven't seen this used much, but it is possible. Option 5 is to just use a string. As seen above, if there is no structure, nothing is forcing us to include the optional value. This could be YAML, XML, whatever. Option 6 is a bit packing method, as seen above with image and point cloud 2, where you just provide the bits and tell the user how to interpret them. Option 7 is composition. Composing messages of other messages is another way to create flexible interfaces. Pose with covariance allows you to use the pose and optionally the covariance. Unfortunately, subscribers can only subscribe to one interface type. If someone is publishing post with covariance messages, you cannot subscribe with a pose subscriber. This leaves you with 3 relatively simple options. Write a translator node that removes the covariance and republishes the pose. Modify the publishing node to publish a pose, either in addition to or instead of the original message. Or 3, modify the subscribing node to have an additional subscriber with the new type. Option 8 is to have multiple overlapping topics. For maximum flexibility, just publish all the variants of the topic that you can think of. Pose, pose stamped, pose with covariance, etc. Go nuts. The smart move is to only publish to topics that have someone actually subscribed. You can save a lot of work by checking the number of subscribers to a given publisher before building and publishing the message. Nav2 publishes the cost maps this way, both as occupancy grid messages and cost map messages. And option number 9 is parallel topics. Before, we had multiple overlapping topics. The same information gets published multiple different ways. Here, we publish all different non-overlapping components as their own topics and use as needed. For example, you could just always publish a pose and in a separate message publish the covariance. This requires synchronization, which can be kind of tricky given the reliability of robot networks, but it's also basically how TF works, where you synchronize each of the TF messages with some geometric type and use the combination to figure out the spatial coordinates. So choosing among the strengths and weaknesses of all these different approaches is one of the primary challenges when it comes to designing ROS interfaces. Finally, I want to wrap up with a couple of criticisms with how ROS 2 specifically handles interfaces compared to ROS 1. So services in ROS 2 have a lot less information than ROS 1. When you call a ROS 1 service, in addition to the response, you'd also get a Boolean return to know whether it was successful or not. In ROS 2, that flag is not set, and you have to include it in the service response explicitly if you want to communicate that back to the calling node. There is a pull request to make a standard pattern that would include that kind of information. And that said, I do appreciate that the Iron release added service introspection, which publishes messages when services are called, making it easier to monitor and debug services as they're being used. But it would be really nice to have that information back. Furthermore, I find actions in ROS 2 are harder to debug. Actions in ROS 1 were based on publishing messages. Actions were started by publishing a goal message. You would monitor them with the feedback message, and a result message would be published at the end. In ROS 2, only the feedback is an actual message. The goal and the result are communicated via services, which can be introspected, but it's not as transparent. I also have a semi-trivial complaint about C++ headers. The headers are further removed from the interface name in ROS 2 and therefore harder to understand. In ROS 1, the C++ include line for the .32 stamped message was include geometry messages / .32 stamp.h. Simply the package name / message name.h. In ROS 2, it's the package name / message and another /, all that's fine, and then the lowercase message name with underscores added in between words. I realize that this is more in line with C++ header naming conventions, but if there's numbers and letters, I can never remember where the underscores go. Python doesn't have this problem. Finally, my biggest personal gripe, many common messages are being deprecated. This is my opinion, and I know that some key figures in ROS disagree with me. There are many simple messages that are marked as deprecated as of the Foxy release. For example, all the interfaces from standard messages that have a single primitive type as their only field. For example, standard messages float32. According to the comments, it is recommended to create your own semantically meaningful message. However, I think it's perfectly fine to have a common set of messages that do not have semantics tied to them. That's what the topic name is for. Furthermore, requiring a bespoke message for every single thing results in additional overhead. Sometimes it's just nice to have a message as part of the binaries rather than have to make a new package for a semantically meaningful interface. I also know exactly what's in a float32 message, whereas I'd have to go investigate/learn what is in a, say, voltage message. In geometry messages, pose2D message has also been marked as deprecated, despite being semantically meaningful. Sure, geometry messages pose has similar data, but it means something semantically different. Since ROS 1, the navigation stack has allowed you to specify the navigation goal as a full 6 degree of freedom pose. However, this is a false promise because it could never process goals in the z dimension nor deal with any pitch or roll. It was limited to x, y, and theta, which is what is contained in a pose2D. I've spent untold hours over the years writing code to convert quaternions to yaw and back again. Pose2D is cleaner, and when I refactored the entire nav stack, I based the entire code base on pose2D and other semantically meaningful 2D interface types. So, that's just about everything I know about ROS interfaces. Hope you learned something about how to design effective messages, services, and actions. If you have any questions, feel free to leave them in the comments. Corrections and additions can be made on the script for this video, which is linked below in the description. We'll call this version 1.0 of the video in case I end up making additional revisions. And remember, the best code is open source code, and the best open source code is documented.